For this week's topic, again, we're continuing with distortion and map projection properties. So, what is distortion? Well, it relates to the unwanted, unreal change of real-world properties. So, this is the Robinson map projection, and we can see here, I'm going to draw, we can see that Alaska is similar in size to Brazil. And Brazil in actuality is 7 times larger than Alaska. So we can see Brazil is at 8,500,000 kilometers squared compared to Alaska, which is smaller in size at 1,700,000 kilometers squared. But based on the Robinson map projection, we can see that Alaska looks similar in size to Brazil. So this distortion is because the way we have used a particular map projection. So we have to remember that the area could be distorted, and we also have to remember a shape of a country can also be distorted when we are choosing a particular projection. Because we are trying to take a three-dimensional surface and we are trying to open it up to make it a two-dimensional surface, we are going to see tearing in the high latitudes like we see here in this example, and we could see also compression close to the equator, and this will make the area of these certain continents to appear smaller compared to the higher latitudes where it's making the area of continents larger, just like we see here in this example. Brazil looks smaller and Alaska looks larger, when in fact it's not that large. And also we could see that there is shearing involved when we are trying to make a 3D surface onto a 2D surface, making it into a 2D surface. And another thing I want to talk about is that there are major and minor distortions. So for a major distortion, you could have the angle or shape preserved, but when you have the angle or shape preserved, you will be distorting the area or the size. And when you're trying to preserve the area, you will distort the angle or the shape. So any map that preserves the angle or the shape, it is called a conformal projection type. And any map that preserves the area is called an equivalent or equal area map. And again, we can have some minor distortions that are preserved along with the major distortions. So when we are making a map projection and we are trying to preserve the angle or the shape, we are also trying to preserve the direction. And most of the time when you are trying to preserve an area of the map, so that we can see the real area of our region, we are also trying to maintain the distance of the scale. So when distance is preserved, it is called equidistant, and when direction is preserved, it is called azimuthal. So for conformal map projection, for conformal projection type, one conformal projection type that's preserving the shape is the Lambert conformal conic. Again, this has a conic projection surface, which is a cone surface wrapped around the sphere. It is a secant case, which means there are two standard parallels, and it's a normal aspect. So it's a normal position of the cone-shaped projection. And this is great for the United States, and this is the basis for the state plane coordinate system. Now let's look at a conformal cylindrical map, and you can see that the areas are not distorted along the standard parallel. Here is the standard parallel, and again, this is tangent case. But as you move north or south, as you move farther north or south, we can see that the area becomes larger and larger. For example, here we have Greenland that appears extremely large and about the size of Africa or even larger. So again, you have to keep that in mind when you're working with these types of map projections. So since it's conformal, it is preserving the shape or angle of the continents, but distorting the size. Like we see here with Greenland, the size is extremely large, when in actuality, it is smaller than that. Next, we have the equivalent map projection. And an example of the equivalent map projection is Albers equal area conic. Again, it has a conic surface projection, and it's a secant case, meaning there are two standard parallels, and it's a normal aspect, so a normal positioning of the cone surface projection. Projection most often used for maps of the United States. So it is good to remember for GIS that you can use Albers equal area conic projection, and you can also use the Lambert conformal conic projection because it is showing the United States or the mid-latitude regions accurately. It's the best fit. But you got to remember that the conformal preserves the shape but distorts the size. And for equivalent, especially the Albers equal area conic, it preserves the size, area, but it distorts the shape. So again, in a map where you want to measure the area, you can use the Albers equal area conic. So again, we can see here for the United States that it appears as a straight line kind of, but this shape of United States is distorted, whereas here we can see this is an accurate representation of the shape of the United States. Again, we could see with the equal area projection that as we move, again, here is our standard parallel. And as you move farther north or south, the shape appears flatter. And we could see that representation here with these circles. The shape appears flatter as you move farther north or farther south. And if you represent Antarctica, like we see here, using the Albers equal area projection, you can see how much flat Antarctica becomes. So it becomes flatter, and this will show us the correct area for Antarctica, but the shape is distorted. So again, the shape distortions are least near the standard parallel, but the shape gets more and more distorted as we move away from the region, like we could see with Antarctica. And then an example of Greenland, Greenland looks flatter as well. So this map projection is called the Robinson projection, and I just showed the Robinson projection from the previous slides. And again, this is a compromise between the shape and the area. So anytime you want to show a region with where you want to measure area or distance, you should not use the Robinson projection, but you should use the Robinson projection for cartographic purposes to show a better depiction of the world. So the shape and area is much more proportional than the Mercator projection because it tries to maintain both the shape and the area. So these are three map projections centered at 39 degrees north and 96 degrees west. So here we have three different maps of the US. One is not projected, which is in neon green like we see here, which means that it is still in the latitude and longitude coordinates. So again, it could be in the degrees, minutes, or seconds format, or the decimal degrees. And this is also known as the geographic coordinate system. And then we have the Mercator, which is the red projection, and the Lambert conformal conic, which is the blue projection. So you can see the difference of these different types of projections and the unprojected. So again, it's very important when you are focusing on a study area, let's say Florida, for example, that each of your data layer is in the same projection. Because if you have a map showing housing and you have another map showing population and you want to overlay these maps on top of each other and they are in different projections, they will look displaced on top of each other, like we could see here for Florida, for example. So it's very important where you have both maps in the same projection. So again, these are examples of unprojected maps, also showing us the geographic coordinate system. So here we have our latitude and longitude in degrees. And here we have zoomed in for North America and the latitude and longitude coordinates. So our geographic coordinate system. For your lab assignment for this week, you will be answering questions based on the difference between geographic coordinate systems and projected coordinate systems. So for reference systems are based on either the geographic coordinates or geographic coordinate systems. Again, we're looking at longitude and latitude coordinates. Or it could be represented based on a projected coordinate system or arbitrary grids. So the two commonly used reference systems are the Universal Transverse Mercator, also known as UTM, and the State Plane Coordinate Systems, which is mainly used for the US. Again, the State Plane Coordinate Systems was created for the United States of America. So it's only applicable for the US. So why create reference systems beyond our projections that we just talked about in the previous lectures? Well, these systems are created to capture even more accuracy and reduce distortion. So here we're looking at arbitrary grids. This is a grid imposed on a map that allows the location of features together with an index. So again, there is no latitude and longitude coordinates like we see here on this map. We only see On the x-axis, A, B, and C, and on the y-axis, 18 and 17. And also there is no projection information here on this map. So here we just are looking for the location of features. So for example, if I want to see the location of Pipestone, I would look at this map and go to B and match it with 17. So again, it's showing us where the location of features are. The GCC map uses an arbitrary grid system to show building locations on campus. So this is the universal transverse Mercator, and we could see here that the zones are each 6 degrees of longitude, and it's numbered as shown at the top from west to east. So again, the UTM is divided into zones, and you can see that for every 6 degrees of longitude, there is a zone that has been created, and then you also have every 8 degrees of latitude. So the universal transverse Mercator coordinate system divides the Earth's surface into 60 zones, like we see here, 0 to 60. And I could zoom in, so 0 to 60. And it's from 84 degrees north to 80 degrees south latitude, like we see here, 84 degrees north, and we could see the equator position here, and 80 degrees south latitude. And it's from 180 degrees west to 180 degrees east, like we see here, 180 degrees west, and then when you go down the map to 180 degrees east. Again, these longitude lines are 6 degrees wide in the north to south columns, and it's described by numbers, and the latitudes are 8 degrees high east to west columns described by letters, not generally used. And this is an internationally standard coordinate system. Again, we have 60 zones. So again, for the universal transverse Mercator UTM coordinate, well, why is this a lot more accurate? Because as I talked about earlier, the standard line is cutting across the area, and the shape is the most accurate along that standard line. In a UTM system, we have created these small zones like we see here in this example. Again, these zones are 6 degrees apart, and among these small zones, we have a north to south coordinate. So we have the equator, and above the equator, this is north, and then we have the south coordinate or standard line that we have created, which we call the central meridian. So now we have very high accuracy in each of these 6 degree zones. Location is described with the zone number like we see here, and direction north or south from the equator. So we could say for the United States, we see zone 10, zone 11, zone 12, 13, all the way to zone 19. And because the United States is positioned in the northern hemisphere, this is UTM zone north. But you have to be specific when your study area is a specific state. So you can see that California falls around zone 10 and zone 11. So if I zoom in here, you could see zone 10 is right here, and zone 11 is right, ooh, I'm not doing a perfect line, but it's that line here. So Southern California falls within which is right here. This is Southern California. Southern California falls within Zone 11 North, so we have to be specific because it's in the northern hemisphere, whereas Northern California, which is right here, falls within Zone 10 North. So again, if your study area is Southern California, you want to use Zone 11 North. However, if you are in Florida, which is right here, you want to use Zone 17 North because 17 North is more appropriate for that location, and it's going to show that area more accurately. Next, we have the state plane coordinate system, and so basically, the system is for specifying positions using planar rectangular coordinates. So it's an individual system of plane rectangular coordinates for each of the 50 states. The state splits into separate zones based on their extent, which we're going to see in the next PowerPoint slide, and zones are projected based on either the transverse Mercator, which is predominantly the north to south extent, as well as the Lambert conformal conic, which is the east to west extent. And this uses feet or more recently also meters, and the scale distortion is kept low. So the government uses the state plane coordinate system particularly for county or municipal databases. So if you have county level data, let's say for example Los Angeles County, you would want to use the state plane coordinate system instead of the UTM. So this was created for mostly United States. So we can see here, for example, if you are in Los Angeles, you will be using the state plane coordinate system zone 5. You'll be using zone 5. You won't be using Florida zone east. And in Texas, for example, you would want to use zone S for south. So each zone is created for accuracy for each part of the state. So again, this is good for county level data. And for the Minnesota state plane coordinate system, if your study area was located in, let's say here, you would want to use Minnesota North, not the Minnesota South.